So when you have done editing to the precipitation, as well as the total cloud cover, you can move on to editing temperature. In many of the end products, temperature might be one of the most important parameters to edit, because it's probably visible in many places. It is extremely important to edit the precipitation and the total cloud cover first, because then if you want to make additions in temperature editing, so that you are saying, for example, that in the areas of clear skies, temperature should be higher or lower. So if you have not done any changes to the total cloud cover, for example, first, you might not see the results as you wish to see. So when you start to do temperature editing, the first thing to do is always to do the verification of the current situation. So you want to know how the models are performing now. In Finland, we have this verification interface that we are using. So we are using bias on map. And here all these individual maps are presenting one weather model and its performance against the observations. The first one here that says meteorologist is our edited data. So we can verify our editing as well. This is for yesterday, because we don't have the observations for today's minimums and maximums available. All the blue dots mean that the model is colder than in the observations. And the red dot means that the model is overestimating the temperature, meaning that in reality the observation is a little bit colder than in the forecast. In our interface, we can also visualize this in numbers. So we can see, for example, here, the difference between the model and the observation is around 2 degrees, and here around plus 3 degrees. Overall, you can quite quickly see that, for example, in the middle parts of Finland, we see these white dots that are within the small error limits. So in this edited forecast, there are more of those when compared to the raw models here. So when you put it in the diagram, you can also see this from here. So the edited data, official data, is performing better. So there is the most of these white values when compared to the rest of the models. But now we have to make decisions what to do next. So how do we edit today so that we keep performing better than the models? So in the northern part, ECMWF seems to be quite okay, and in the rest of the country, EC has probably the least amount of these errors. So maybe you can use EC as a base and then modify that according to, for example, total cloud cover. So maybe in this case, we don't need to blend any models, which you can do. We have done it with total cloud cover as well as with the precipitation. But now that it seems that ECMWF alone is performing a little bit better overall when comparing to the other models, I think we can stick to it as a base. So now that we know that we can have ECMWF as a background model, we already have that because we loaded ECMWF data to be our edited data in the beginning. So I'm gonna go to row number 3 because that's the next in order. So here I have the temperatures. And there are multiple ways to edit the temperature. For example, you can blend the models. But if we want to do editing in more specific situations, then you need to do more manipulation with smart tool language. So, for example, making the nights colder over higher terrain. So you have to refer to topography. And here's an example of that. So we have if and else if structure. So that if we have a mountain that is over 1 kilometer, so 1000 meters, and total cloud cover is less or equal to 60%, and elevation angle is less than 0, meaning that it's nighttime. We can make changes so that from the current temperature at any point, fulfilling these conditions, minus 3 times ramp down function according to the cloud cover. This is actually quite clever because it combines the information from total cloud cover and then puts it together with the information of temperature. So here we make biggest changes to the temperature when our total cloud cover is less than 20%. So we are decreasing the temperature by 3 degrees in those cases. And then it's going to be a gradual change from 20 to 60%, and after that there will be no change at all. And then we have another condition in cases if our topography is over 500 meters but less than 1000 meters. We don't have to write it down explicitly because this condition else if is not run if the first one is fulfilled. So in cases where the topography is over 500 meters and otherwise we have the same conditions as above, we are decreasing the temperature over higher terrain by 1 degree if the total cloud cover is less than 20%. So in the clearest situation. And we can try to see what happens. So let's visualize a time where E angle is less than 0, so it's nighttime. So let's try, for example, 00 UTC time. And let's see if it makes some changes here. It made some changes here over Sweden. So pay attention here when I undo. You can see that some values are changing also in the Norway. We don't have any big hills or mountains in Finland, so that's why the changes are in Sweden and Norway. So that was way number 2 to make these changes. There is also another way. So let's try that now. So we can leave that change there because it made sense. So let's have it there and let's try another thing. So just before we were decreasing nighttime temperatures according to the cloud cover. We can also increase daytime temperatures according to the cloud cover. And here is an example of that. So basically the idea is exactly the same, but instead of using E angle, I can just use local hour, so L hour. So instead of UTC, this really applies your local time zone. So L hour larger or equal to 10 means really 10 AM local time. And with this kind of manipulation, I'm once again stating that if the total cloud cover is less or equal to 30, we're gonna make the bigger change, so 2 degrees addition to the temperature. And then once again, I'm referring to the total cloud cover. So in a case, it's really very clear situation. It's gonna add the daytime temperatures by 2 degrees in those locations. And then another condition, not so strict. So we are allowing total cloud cover to be less than 50%. And then we're gonna make a change to the temperature according to the cloud cover where we have different limits there. So once again, we can run this using the whole selected area on the timeline because we have the time covered here in the code. And once again, I'm gonna do the change to the whole area, so not using selected points and just execute. Let's visualize the time that is showing potentially some change. And once again, we saw some change. I can now go to row number 2 to see where I have the clearest skies. So here. And now going back to row number 3. So I should be seeing some changes here. So if I undo, I can definitely see some changes to the temperatures. And if I redo, I can see them getting higher, which is definitely making sense if you look at the code. So this is also quite a good change, so let's use that and let's not undo it either. But now that we are using local hour, there is a possibility to make a mistake with this, and it's related to the nighttime. So I will give you an example where you have to be extremely careful what word to use here. So for example, if you want to do changes during nighttime and you want to refer to local hour, you can do it, but you have to be extremely careful. It should be done using the word or instead of and. And the reason is that mathematically speaking, you cannot have an L hour value that is at the same time larger than 20 and smaller than number 6. So you have to use the word or here in the middle. And it won't hurt to use some extra parentheses here around these L-hour values. And I'm having the same condition in both of these if and else if clauses. Otherwise, it works just fine. Just remember to pay attention to the word you're using here. So this code could be run during the nighttime, but since we already did some changes there that I am happy with, I'm not gonna use this code, but as an example, I can of course run it. So execute. And now you can see some changes. So if I go back, I can see that there we had some positive values here. But now after this code, they are negative. The reason is that the change I'm making is quite big, so it's even 3 degrees in the cases where we have total cloud cover less than 20%. And if you look at the cloud cover I've edited already, you can see that there is quite a big hole in the cloud, especially in this area. So that's why these areas are getting colder quite a lot. But this change I'm gonna undo because, like I mentioned, I already did some changes and I don't want to make changes that might overlap each other. But there is also another way to modify the temperature. And maybe a more advanced is to use SmartMet's ready-made function called duration. And here we have an example of that. So duration function is calculating the time in hours that how long this condition that we put here is fulfilled. You can find more explanation about this duration function from the manual. So here I'm gonna assign the value from the duration function to my new variable called low cloud duration. So the value that is assigned to this parameter is telling me how many hours the total cloud cover is less or equal to 50%, and the amount of time it is checking backward from our current time on the timeline is 4 hours. So if it's more than 3 hours, I'm gonna make the temperature colder the most, so by 4 degrees it's quite a lot. But especially during the wintertime in Finland, the model errors can be quite big. And then not so strict conditions, so if it's over 2 hours, the temperature is made colder by 3 degrees, according to the cloud cover. So that the biggest change happens when there is the least amount of clouds. We also have these extra conditions about wind speed. They're important if we are thinking about low-level inversions and distance to sea, so we should be further away than 2 kilometers. We can try what happens, but now note that it's not referring to local time or the angle or anything related to time, so now I have to choose the modification period from the timeline. And let's say that I want to try this for this closest night, for example. So I'm gonna choose this area on the timeline and then execute and see what happens. It made some changes over here and also in Norway. So this is quite usable during autumn and spring especially, but of course why not during winter time as well. You might need to modify these constants a little bit so that the changes might be bigger, but the overall idea is the same. And once again, I've already done some changes to the nighttime, so I'm not gonna leave this change here, so I'm gonna undo it. In case you have some fractal data available in your country, you can use that information on your benefit. So we do have some fractal information in Finland, so I can make changes like this, for example. So the fractal data is not something that I can refer to directly using abbreviation. But like you remember, using this dialog here, you can always refer to these ID numbers and then refer to those parameters you wish to refer to. So I know, for example, that fractal 50 is parameter number 874. And if I want to refer to ECMWF, I just write _EC. And now I can write it as a part of a script. So parameter 874_EC 30%, and otherwise my edited data by 70%. And this is especially useful maybe in the end of your editing, because models tend to have more bias in the end. And you can actually check this if you go, for example, to ECMWF webpage. So you can see these meteograms where you can see ensemble runs. This thick pink line here is the operational run that we are visualizing on SmartMet. It's not spreading too much in this situation, so the predictability is quite good up to almost 10 days. But you can still see some deviation. So maybe from Thursday night forward, you can see that these individual members are spreading a little bit. And then in the end here, this operational run is making a dip that is making it colder than basically any of the ensemble members would suggest. So this is something I would want to correct in my editing. So I would use fractile 50 to make it be more averaged over these individual members. I have a visualization where I have southern part of Finland, one meteogram for the central part of Finland, and then one to the northern part of Finland. And in all of them, I can see the same information that maybe from Thursday night onward, I could use some ensemble information. So what I'm gonna do is that I'm gonna first select the whole edited data area, and then go to Thursday night, and to this latter part, I'm gonna run the script. So I'm gonna add some information about the fractals and hence about the predictability of the situation there. So I'm gonna run it to the whole area again, so execute. And you can see some changes happening. So if I undo, some of these points are getting a little bit warmer because we saw that kind of colder bias. I'm gonna leave it here because I'm happy with this change. Remember that when you have done some changes to temperatures, you might need to change your precipitation form. So pay attention so that your precipitation form wouldn't be unrealistic if you, for example, need to increase your temperature by multiple degrees. So it might be a good idea to write sort of a checking script that you run after you have done changes to your temperatures. So in addition to Smart Tool language and what you can do with that to the larger scale, you can also do point-wise editing using the control points. Especially if you're trying to visualize temperatures in points that are, for example, largest cities, it might be wise to do also some point editing so that the data looks correct and so that it is in the way you want it to be. Also, you might have some phenomena in your country that requires you to do something specific with Smart Tool language regarding the temperatures. And you have the tools. You have the SmartMet and you have the Smart Tool language. And if you wish to get some ideas, you can always check the manual for what kind of functions or parameters you have available.